Hello everyone, welcome to the video answer key for this worksheet on partial pressures. So the first three questions, 1, 2, 3, is just based on Dalton's law of partial pressures, and then the mole fraction and the collecting gases over water displacement is a application of Dalton's law of partial pressures. So first of all, let's go ahead and do number 1. So here I have a tank that's pressurized to 5 atm. If 18% of the moles are hydrogen, 49% are argon, and 33% are krypton, then what are the partial pressures of each gas? Now, because the number of moles, now one thing to note right away is that since we have three different gases here, hydrogen, argon, and krypton, and they're asking for the partial pressures of each gas, you know that you need to have three different answers. So, then I am going to go ahead and do the calculations. Now, knowing that 18% of the moles are hydrogen, what this means is that the partial pressure of hydrogen is also 18% of the total pressure that's in the tank. And that is because of the fact that partial pressure is only dependent on the number of moles. So, I'm going to go ahead and write my equation. I know the partial pressure of hydrogen is just the 18% of the total pressure. And I know that the total pressure is 5 atm. So I'm going to do 18% converted to decimal point. And the total pressure is 5 atm, giving me the final answer to be 0.9 atm. You're going to follow the same exact step for argon and krypton. Now, after you've done this, I'd like for you to actually check your work, because this is one of the instances where you can actually check your work to see whether you did it correctly or not. And the way you do it is that you are going to add up all the numbers you just found. And you'll find that if you did your calculation correctly, this should come out to be the total pressure, which in this case is 5 atm. So, and indeed, we do have that number right there. So, our calculations are correct. So I'm going to go ahead and box them now, just like that. All right, let's go ahead and do number 2. So for number 2, here I have argon makes up 0.93% of the atmosphere. In a given sample of air, aka the atmosphere, because the atmosphere has air in it, the partial pressure of argon is 6.54 millimeter mercury. So I'm going to go ahead and just label it as partial pressure of argon. What is the pressure of the sample? Now, this question kind of spin the first question on its head a little bit by they actually give you a partial pressure of one of the gases within that sample, and they're asking for the pressure of the sample, aka the total pressure. So now I want to set up my equation to reflect what they've given me. So here I know the argon makes up 0.93% of the total sample. So here I have partial pressure of argon is 0.93% of the total sample, which is the total pressure. Because remember that partial pressure only depending on moles, and argon makes up 0.93% of the moles of the atmosphere. Now, it doesn't explicitly say mole, but you should know that it's implied, because the only way for you to calculate some kind of chemical within a sample is by the quantity is always moles, unless specified otherwise. Okay, so then this would give me, I actually already know what is the partial pressure of argon. So I'm going to actually rearrange this equation. And because I want to find P total, I'm going to say P total is equal to partial pressure of argon divided by 0.3%, which is 0.0093. So I'm going to just go ahead and plug this in. 703 millimeter mercury. Now I just want to touch base on number 3 real quick. Here I have a tube containing 3 different gases here. The total pressure is this much, and you know the partial pressure of hydrogen and helium. So now it's just asking you for the partial pressure of oxygen gas. So I like to just set this up and then you can finish it up. The partial, I know that the Dalton's law of partial pressure is P total equals to the partial pressure of all the gases in that container combined. And I know that we have partial pressure of hydrogen, partial pressure of helium, and then partial pressure of oxygen gas. And I already know the partial pressure of hydrogen and helium and the total pressure. So I'm going to plug it in. I know hydrogen is 75 and helium is 240 and the partial pressure of O2 is remaining. So you can go ahead and rearrange this equation to give you PO2 to be 108 atm. Let's go ahead and do mole fraction, where it's a different way for you to find the partial pressure of a gas that's within a mixture. So I'm going to go ahead and do number 4. So for number 4, I have here a flask containing a mixture of this many moles of hydrogen gas and this many moles of oxygen gas. If the total pressure is 1304 kilopascal, what is the partial pressure of each gas? Now, as I said here, because you have 2 gases, hydrogen and oxygen, and they're asking for the partial pressure of each gas, you have to have 2 different answers boxed. Now recall that the mole fraction is X, and I'm going to say this is some kind of gas number 1, so I'm going to say X of 1 is equals to the moles of 1 of that particular gas plus E over the total mole. And then I also know that the partial pressure of, say, that gas number 1 is actually equal to the mole fraction of gas number 1 multiplied by the total pressure. So here I have given to me number of moles for each gas. So I can find the mole fraction, and then I also was given the total pressure here. So that's my P total. I can also now find the partial pressure by just plugging in the equation. So I'm going to first find the partial pressure of hydrogen gas. And that's going to be 1.324 moles of hydrogen gas over, I know my mole total is 1.24, which is of hydrogen gas, combined with the mole of oxygen gas, which is 2.91. And that should give me 0.2987. Remember that there's no unit for mole fraction, so we're going to just leave that number as is. Then I'm going to find the partial pressure for hydrogen by plugging it into this equation. So I know that the mole fraction is this much, which is found. I'm going to multiply by the total pressure, which is 104 kilopascal. And your final answer is 31.1 kilopascal. Boxed. And then let's do the same thing for oxygen. So we're going to do X of O2 is equals to 2.91 mole over the same total, like this. So that should give me the answer of 0.71012. And same thing, I'm going to find the partial pressure of O2 by multiplying that mole fraction by the total pressure, and that should gives me 72.9 kilopascal. Let's look real quick at number 5. I want to set this up, or at least tell you the strategy of how to approach it, and then and then you can work it out on your own. For number 5, instead of giving you all the moles number of each of those gas, I'm actually give you the mass. So that means that you're going to have to take a little extra step to find the number of moles. So here I have 7 grams of CO and 10 grams of SO2. This mixture has a pressure of 0.33 atm. I'm asking what is the partial pressure of each gas. And once again, two gases, CO and SO2. Two answers. So step number 1 is for you to convert a gram of CO to moles of CO using the molar mass. And you're going to do the same thing to gram of SO2 and convert that to mole of SO2 using the molar mass. Step number 2 is for you to use those moles number that you just found. So use moles number from number 1 to find the mole fraction of CO and the mole fraction of SO2. Then number 3 is for you to use the mole fraction of CO and SO2 to find the partial pressure of CO and partial pressure of SO2. So just follow these steps and you should be able to get the answer that's in the answer key. In fact, one of these we have already done in class in one of your notes, so you want to take a look at your notes to see how that's done. Go ahead and do that. Now I want to go over number 6. So number 6 is just similar to number 4 and 5. It's just getting to the numbers of moles is slightly different in this case. So I want to go over it real quick. And here I have 200 grams of sugar or sucrose that are dissolved in 2 liters of water. So here I have 200 grams of sucrose, and I've given you the chemical formula for sucrose. And then I said you want to dissolve the sugar in 2 liters of water. And it's asking for what is the mole fraction of sugar in water in the solution. Now the mole fraction of sugar, so they're asking for 2 of them, so you know you have to have 2 answers. And so in order to get for the mole fraction, you need to know the moles of sugar and the moles of water that's present in this container. Now I'm going to first go ahead and convert 200 grams of sugar to moles by using the molar mass. And you can either do this by calculating the molar mass yourself using the periodic table, using this chemical formula, or you can kind of look it up as well on Google, and it should give you 342.3 grams of sugar, roughly. That's per mole. Then you should get an answer of 0.5843 moles of sugar. And then you're going to do the same thing for a liter of water, but I want you to pay attention to what I'm doing with water. I was given 2 liters of water, and then I want to convert it to moles. And remember, the conversion factor that I have you basically repeat to me all the time is that 1 mole of any gas is 22.4 liters. So in this case, it's 1 mole of water. It's 22.4 liters of water. So then you can actually use this conversion factor and tell you what is the go for straight from liter to moles. That should give you 0.0893 mole of water. So now you can use these moles to find the mole fraction of, for in this case, it's mole fraction of sugar, and then you're going to use the mole fraction to find the partial pressure of sugar. And then you can do the same thing, use this mole to find the mole fraction of water, and then find the partial pressure of water, just like that. Let's go ahead and go through a couple problems that involve the little contraption experiment I showed you in class. So how you would collect gases by displacing water in a tube. So I have just number 7 and 8 for you. Number 7 is very similar to one we did in class in the notes. So take a look at your notes. It should be very, very similar. So you can kind of do something similar there. I want to go over number 8. And just remember that the Graham's law, so number 9 to 11, are no longer going to be on your test, so you are not required to do it on your homework as well. So let's go ahead and go over number 8 for collecting gases by water displacement. So here I have a sample of hydrogen that's collected over water at 25 degrees Celsius. I'm just going to go ahead and start underlining things I see. So that's temperature, where the vapor pressure of water is this much. So vapor pressure of water. So I'm going to go ahead and label that. The water, pressure water. The volume occupied by the gaseous mixture is this much. And the total pressure is this much. So I'm going to say that's the P total. Calculate the partial pressure of H2 and the number of moles of H2 present. Now remember that when we were doing the little contraction and when you collect the gas in a tube, the tube always contained both hydrogen, or in this case hydrogen, or any gas that we're trying to collect, and water vapor. That's why we have to use Dalton's law of partial pressure to figure out the partial pressure of that gas, because we're only interested in that. We're not interested in the vapor pressure of water. So that's number 1. Let's answer question number 1. So question number 1 is partial pressure of H2, and then question number 2 is number of moles of H2 present. So then to answer number 1, I'm going to say that I know that the total pressure in that container or in that tube is the pressure of water and the pressure of the hydrogen gas. So, and I know that the partial pressure is actually already been given to me, which is this. And then I know that the partial pressure of water is 23.8 torr. Now I need to convert this torr to ATM because I need to, they have to be in the same unit, otherwise that would not work out. So first I'm going to actually convert this. So 23.8 torr. I know that 1 ATM is actually 760 torr. And that actually gives me 0.0313 ATM. So I'm going to go ahead and plug this in here. And I have my partial pressure of H2 is left. So I'm going to say that partial pressure of H2 after just doing a little algebra should gives me 0.0918 ATM. I'm going to go ahead and box it now because that answers my first question, which is partial pressure of H2. I'm going to give it a check mark, saying that I'm already done with that. Okay, number 2. To answer this question, I need to know the number of moles of H2 present. Now I want you to note that we have here the partial pressure of H2, which is found here. And then I have the volume, which is this much. And then I have also the temperature. Now what that means is that I can actually use the ideal gas law, because the ideal gas law, recall, is PV equals nRT. And I have already been given 3 out of these 5 variables, and I know R is always known. So I was already given pressure, and volume, and temperature, and R is always known. So I'm going to give that a check mark too. So then I'm just going to go ahead and solve for moles, just like what they want in the question. So I'm going to rearrange this equation to N is equal to PV over RT, and I'm just going to plug this in. So if you did your calculations correctly, you should get the answer of roughly about 1.88 10 to the negative 2 mole of H2.